This is a dramatic reading of Deriving the Unified Gem Field Equations, the fifth of 5, a blog by the Stand-Up Physicist, available at science20.com. The diligent reader or viewer of this mini-series on fields, which comes to a close with this post, will actually know what's coming. Lagrange density will be defined. The Euler-Lagrange equations will be applied to create the field equations, and then something about gauges will be said. And this is actually the simplest of those done so far, having only 12 terms in the Lagrange density instead of like 18 or 22. There's nothing grand about this process. No extra dimensions peek in from peekaboo brains. The simple math swings out the strange here, so making the gem field equations glitter. There is one word in that title that might cause controversy, and that word would be unified. There's already an equation which, for gravity and electromagnetism, that unifies the two, and it's right there. It's known as the Hilbert-Maxwell action, and or that's actually the Lagrange density there. And it's basically a combo meal of our two best theories for gravity and electromagnetism. But there's like literally no give and take between those two. We got R's, and the other term doesn't have a single R, and J's and A mu's, and addition just isn't enough to say we've unified like anything. So it's easy enough for me to follow in the footsteps of failure, and the way I would do that is by taking two Lagrange densities that have showed up in this series here. The one for EM, written in the quaternion form, but when you write it down into its components is exactly the same as the standard guy. And then my proposal for something that would work with gravity, which would be this hypercomplex thing with those box time symbol being hypercomplex products, or sometimes I call them California products. They're all positive, but otherwise the rules are just the same as quaternions. And if I just added those two together, well, so what? So actually, let me go a few comments on that nomenclature there. The times symbol there, the X was for quaternion product. The box time is for hypercomplex or California product, defined in the video blog before this one. It's really like a quaternion product, except no minus signs are used in the generation of the product. So then there are the three players, which would be the 4 current density and the 4 potential A, and then those upside down triangles, which are actually covariant for derivatives. Now, the Lagrange density for the EM source equation can be used to derive the two Maxwell equations. That would be Gauss's law and Ampere's law. And I did that in 2 out of 5, as it were. The hypercomplex gravity equation Lagrange density was used to derive an updated form of Newton's field theory for gravity. And there actually has been a little bit of controversy in the Science 2.0 blog, because there are people, somebody there that didn't really think that I'd achieved a certain goal, particularly that I hadn't kind of come up with a differential equation that kind of defines what the metric must be, because it's not what's called I don't have a metric theory, which really has to be at least a rank 2 tensor. I have this rank 1 tensor, so it's like, how does this make sense? Well, what I said was that I've got this metric potential theory duality, which is a new idea out there. And so if you were to work in completely flat spacetime, like that very first equation, which was basically kind of a way to write Newton's law, you really would make no progress, okay? Because, I mean, you could solve it for the potential, but those this curly kind of differential things are what you learned in high school. You know, it's just dx, dy, dz, and there's kind of no place to manage change a curved spacetime. So for a spacetime that's ever so slightly curved, though, which is the state of nearly all of the spacetime in the universe, you know, you can treat one of those guys as a covariant derivative, okay? And that's that upside down triangle. And officially that has a connection and the differential element that you learned in high school. It's that connection which, if metric compatible and more torsion free, is called the Christoffel symbol of the second kind. And those are technical criteria that are used also in general relativity. And the Christoffel symbol has first order derivatives of the metric. So since we're taking derivatives of that, we actually have second order derivatives of the metric. And it's that equation, along with a similar hypercomplex law equation, that has the metric, say the exponential metric solution. And I've got a different blog out there about that one. And I actually have a friend who went ahead and showed that the exponential metric does solve that middle equation. Now the equation at the bottom, that has two covariant derivatives, and that form is going to apply when you have an exceptionally strong yet static field, and I haven't found a metric solution for it. Why? Because my skills are finite, time is finite, all that kind of stuff. So this blog is going to proceed on the assumption that the hypercomplex gravity equations are valid and an interesting competing alternative to the Einstein field equations which show up in general relativity. A good unification of gravity and the three other forces of nature would be, I don't know. No one knows at this point, right? We don't have one. And it's really kind of hard to come in here without some bias about, you know, answering that question. Well, one point is that just doing gravity and EM is not going to be enough, because you really do need to think about the weak force and the strong force. You know, how are you going to include those sorts of things? So there's basically like no pattern to how you unify different fields in theoretical physics, because what we can look at is other examples for gravity. So for electricity and magnetism, this is a way of viewing it. And if you put things as a potential theory, then you can write out both terms for both E and B. And actually, traditionally, one doesn't use the quaternions here. Instead, you say something like, no, these are all part of the same second-rank antisymmetric field strength tensor. It turns out to be saying the same thing, but that's the way it's usually phrased. Unification of EM with the weak force is actually done with group theory, describing EM as a group and the weak field as a group, and then saying, hey, look at these guys work together. Now, general relativity, with its lonely Lagrange density consisting of, the Ricci scalar R, has turned down all proposal by the brightest minds in physics for almost like 100 years. So I say it is time to leave that beautiful bitch at the altar. You know, some women are just not the mating type. You know, see Lady Gaga's nuptial bed at the end of her video, Bad Romance, if you want to see what who you should not bring home to mama. So, you know, when climbing at this high altitude, unification, whoa, the air is very thin here, and it's easy to fall off all sense of reality. It's important to take kind of a gentle approach. And so I'm going to ask a different question, which is related to mass and the other forces of nature. And that question is, what does that Higgs mechanism accomplish? Now, right out of the box, the standard model has particles with zero mass for all. I mean, it's very nice and general in that way, including all the bosons. And that works fine for, like, photons and for gluons, but not for the 3 bosons that appear in the weak force. The 2 W's and the Z need to gain some mass in a way that does not break the symmetries found in the Lagrange density. And why not? Well, because if they did break that Lagrange density kind of symmetry, then we could see that those charges were not conserved. And we've actually done experiments to show that, yeah, electricity is conserved to the highest degree that we've been able to imagine testing it. Okay? So we really got to preserve that. Now, the Higgs mechanism leaves that Lagrange density untouched. Doesn't get anywhere near it. Instead, it uses this Mexican hat trick, a spontaneous symmetry breaking of a false vacuum by the scalar Higgs field. So just like that game Clue, the LHC collider, that's redundant, the Large Hadron Collider, knows where Professor Plum must have used the candlestick to foil high-energy physicists for decades on end. 119 GeV. That's where the money bid is. We're talking, what, October of 2011. Bookies in England actually will not take a bet on finding no Higgs. You know, we're going to find it. We're going to find it. And yet that's the bet I want to make. You know, no goddamn particle. Not now, and not in the near future when we have 5 inverse femtobarns of data from the LHC. That's what I'm betting on. So the basic fields all have gauge fields, either using the California or the quaternion products. And you can see 4 of them here. The top 2 are the California products, and I do it with conjugating two different ways and getting different combinations of the E and B field, small e and small b field, but the same G. And then when I take the differential and use the quaternion product against this potential theory, potential, I end up with the same G, and then it's the B field that decides to flip signs. So no matter how the 4 derivative and 4 potentials are multiplied together, the first term of the product is the same. It transforms actually as the diagonal of this delta mu a mu. That's for those who are more familiar with tensor notation, but it's not a Lorentz invariant. So this is a perfect setup for a perfect cancellation. In blogs 2, 3, and 4, the gauge field was wiped out. The first thing. That's what I did. This time, though, I'm going to keep it. Okay, so I'm going to rewrite the Lagrange densities, including the gauge. So here first is this hypercomplex thing, and I've got my two orderings of how I do the conjugation, and I've got the G's there before I would wipe them out, and now I write it all out, and you go, whoa, that's a pretty complicated looking phase. Here is what happens in EM when I don't wipe out the gauge. I've got the two orderings of A and del, and I get these G terms, and again I get this incredibly complicated phase. So those phases, I think, are worthy of study. And when I have a small army of graduate students, I promise to do so. It looks like fertile soil because it's got this pointing vector that just shows up by happy accident. For now, though, I will follow the rules laid down by Einstein's summation convention and actually ignore the phase terms. So we're going to now define the gem Lagrange density by subtracting one of these from the other and focusing only on the scalar parts. And there it is. I've got the two E fields minus the two B fields, and that's about it. The gauge field is gone completely due to this perfect cancellation. And there are four distinct field strength tensors, or four derivatives of a four potential A that are part of here. And each one is gauge dependent. And that means that they are relevant to particles that have mass and are unable to travel at the speed of light. Yet the overall Lagrange density is invariant under any gauge choice because of those cancellations. All this happens at the level of the Lagrange density, not at the level of finding spontaneous symmetry breaking for solutions. So, as has been done before in my blogs, the Lagrange density must be written out in its component parts. We've done that before, so let's just copy in these results. We need to toss in a minus sign for each of those to get the gem Lagrange density. Only the mixed terms have the opposite signs will cancel, and so we're basically ended up with these squared terms, like so. So now we're going to go through that machinery that we've done through this entire series. We're going to focus on B. And as you can see, and probably expected, they're all the way over on the right-hand side. And there are only three of them. Oh, so this is easier. So we apply Euler-Lagrange to that, and we just get this del. Oh, there is no current coupling. That's easy to deal with. So we can summarize this whole thing in terms of the fields as being these two fields. We just kind of add them together, and that's it. So now we want to do something Ampere-esque like. So we focus on AX terms. And yes, there are three terms, one per row. And we apply Euler-Lagrange to get this neat kind of expression here, where we've got this dAx, and it doesn't have a dx. It's everything but dx in there. And we can summarize that, what's going on there. That looks fairly complicated, particularly compared to when you write out the component parts. So if we compare the two laws, we just end up with these kinds of expressions, and we say, that looks vaguely familiar. Why? It's because it's on the t-shirt. It's literally there. Del squared phi dAx second derivative AI dt dAI dxj dAI dxk equals 0. So if you want to wear it, you gotta pay the big money. I think usually around $15 plus $3 worth of shipping. Okay, so there's just a lot to talk about. Actually, the issue is that there's so little to talk about. I mean, front row and center is that 0 for the current coupling term. That's just, it's just not there. I mean, whatever this is, this is something. It can't be about EM, right? Because there's no home for charge. Well, look, physics doesn't need Maxwell 2. Since the Maxwell equations have stayed like rock solid through decades and actually more than a century. The gem field equations don't encroach on that kind of turf. there's also no mass density. So it can't be really about gravity, can it? I mean, gravity requires big honking sources, and zero is not big. So if we bring together force where like charges attract, that's a gravity-like thing, with like forces that repel, that's an EM kind of thing. Well, that's kind of a conflict, you know? So maybe that zero is a good thing if you're really somehow trying to bring these things together. Well, the GEM field equations are not grand. That was promised, right at the start. They do appear, at least in my eye, to accomplish two feats. The first is to offer an alternative to the Higgs mechanism. A gauge field is included and then canceled away in the same Lagrange density. I mean, that's what GEM does, you know. The second bit of math magic is a field theory justification for the equivalence principle first outlined in general relativity. The terms that are used in the California product house the gravitational mass that lead to the hypercomplex gravity field equations. The terms that are in the quaternion product house the inertial mass. You know, that goes to the Maxwell equations. Now that's EM, and I didn't say anything about the weak field, but the way you get there is, since you've got a quaternion, you could actually substitute a normalized quaternion, which would be U over the norm of U, and therefore it would have that symmetry throughout the whole thing. And the way I'm hoping to step out to the strong force is basically having two quaternions go in there, one conjugating, and maybe that will be rich enough to pull off the kinds of stunts needed for the strong force. I feel tenuous about that, but at least it is a possibility. So here's a property about this that surprises me to this day, and I have no idea what it means, but it sounds deep. There's this, there are these technical quantum field theory books, and they just go on and on about gauges, right? And it seems, like many of the most important Lagrange densities are invariant under a gauge transformation. Examples including, of course, the Hilbert and Maxwell Lagrange densities, the stuff underlying general relativity, underlying electromagnetism. Now, all the Lagrange densities that have appeared in this mini-series have also had that property, invariant under a Lorentz transformation. And now the GEM field equations are also invariant under a gauge transformation. Unlike the field equations for Einstein or the Maxwell equations themselves. You change the gauge for Maxwell, you change the field equations, okay? So what does it mean that the field equations are, remember, it's the field equations are independent of gauge choice? That's what I don't know. If being invariant under a gauge transformation is like this deep idea for the Lagrange density, that might also be the case for these field equations. So here's my snarky puzzle. I doubt it's meaningful, but do the sum of these gauge-dependent Lagrange densities instead of the difference. Practice this kind of technique. And someday those equations might solve a deep mystery or not. Okay, thanks a lot.